All right, welcome to this definitive explainer designed specifically for you A-level OCR geography students who are actively aiming to lock down that A-star grade. We're mastering coastal systems today, zeroing in on Section 2.B, those absolutely critical high and low energy case studies. We are going to break down everything you need to know using authentic study notes and the official syllabus parameters.
Okay, let's establish the rules of the game straight from the OCR syllabus so we know exactly how you're being assessed. For this physical systems component, you've got AO1, your core knowledge and understanding, making up 10% of the overall A level. AO2, which is your ability to apply that knowledge to evaluate issues, carries a 9% weighting. And AO3, your investigative and data skills, sits at 3%. The big takeaway here, you can't just memorize facts for top marks. You have to synthesize and apply them.
Here is our mental roadmap for today. 1. Cracking the assessment objectives. 2. The high-energy Yorkshire coast. 3. Interrelated high-energy landforms. 4. The low-energy Nile Delta. 5. Delta landforms and sediment. And 6. Human impacts and vulnerability.
Section 1. Cracking the assessment objectives and knowing your systems. To really nail those AO1 knowledge marks, we first have to define the fundamental systemic difference between our two environments. A high-energy coastal environment is totally dominated by destructive waves driving massive erosion. Think rugged, rocky landforms. On the flip side, a low-energy coastal environment, like an estuarine zone, features shallow waters. These shallow waters literally drain the incoming wave energy, which leads directly to intense sediment deposition. It's essentially a grand battle between wave power and sediment supply.
Section 2. High-energy Yorkshire coast, the engine of erosion. Picture the North Yorkshire coast. This environment is almost entirely dictated by its North Sea exposure and the dominant wave directions barreling in from the north and northwest. The areas nearest to Saltburn are incredibly exposed, meaning they get hammered with the absolute highest inputs of raw wave energy.
Now, the crucial metric you want to remember here is the fetch. We are talking about an uninterrupted fetch distance of over 1,500 kilometers across the North Sea. Because the wind is blowing over such a massive expanse, the wave heights along this coastline frequently blow past 4 meters. Just imagine the sheer hydraulic action and abrasion power of a 4-meter wall of water constantly crashing into a cliff face.
You know, examiners absolutely love specific data. So memorize this stark contrast in erosion rates. Why do the rates vary so wildly? It's largely due to variations in geological resistance. Weaker shale and clay erode quite fast, at an average of 0.8 meters per year. Meanwhile, the highly resistant sandstones and limestones erode at just 0.1 meters per year. This massive geological difference creates a remarkably discordant coastline full of prominent headlands and deeply recessed bays.
Section 3. Interrelated high-energy landforms in shaping the coast. Because of that extreme geological variation we just talked about, geology completely dictates the topography. Down at Flamborough, you have these incredibly strong, tightly bonded chalk rocks that form towering vertical cliffs 20 to 30 meters high. But if you move between Saltburn and Robin Hood's Bay, the geology softens up. You get these gentler, stepped profiles, because the waves easily hollow out the weaker clays into deep bays, while the tougher rocks are left protruding out into the sea.
To really show off your process explanations for AO1, you'll want to track the exact chronological evolution of the landforms at Selwyk's Bay. First, high-energy waves exploit the natural joints and faults in the chalk. Over time, these widen into sea caves and eventually arches. When the roof of an arch inevitably collapses, you're left with isolated stacks out in the water. A perfect one to name drop is the Green Stacks Pinnacle. Add in some vertical master joints getting hollowed out into massive funnel-shaped blowholes, and you've got the whole dynamic system.
You'll also need a rock-solid example of a shoreline platform, and Robin Hood's Bay is your go-to. Lock in these specific metrics to guarantee those knowledge marks. This platform is carved directly into the lower Lias shales. It has a very gentle typical slope of just 1 degree, though it ramps up to 15 degrees in some spots. It stretches an impressive maximum width of 500 meters offshore, and it's been actively forming for the last 6,000 years during periods of steady sea level rise.
Section 4. Low energy, the Nile Delta and the delicate balance.
Okay, massive gear shift here. If Yorkshire was all about the brute force of the waves, the Nile Delta is a complete masterclass in delicate sediment distribution. Running parallel to the Mediterranean coast, it's fed by a mind-boggling river catchment size of over 3 million square kilometers. Unlike the deep North Sea, the shallow Mediterranean shelf forces incoming waves to lose their energy, which makes the water drop the immense load of sediment it carried all the way from Central Africa.
We are talking about an absolutely staggering 91.3 million tons of sediment yielded annually, primarily from the Blue Nile in Ethiopia. Historically, this number is what built the entire delta system. It is the absolute lifeblood of a low-energy coastal system. Without this continuous, massive input of material, the landform literally cannot sustain itself against the sea.
To truly demonstrate that A-star level retention, you need to break down the precise composition of that sediment. The suspended load is incredibly fine: 30% clay, 40% silt, and 30% fine sand. Because it's so fine, the river can carry it for thousands of miles. But the exact moment the river hits the sea and loses momentum, this precise mixture settles out and builds the delta structure.
Section 5. Delta landforms and sediment. Building the coastal plain.
Notice how the system essentially sorts and deposits this material into three very distinct parallel zones running along the coast. Right by the water, the foreshore plain features elongated ridges alternating with lagoons and salt marshes. Move a bit inland to the frontal plain and you'll find scattered eroded limestone outcrops in clay. Keep going south and you hit the sandy zone, which is packed with diverse sand formations like dunes and massive sand sheets.
Longitudinally, the river's physical layout changes dramatically. It actually splits into distributaries over 160 kilometers inland at Cairo. What's really incredible is the depth of the alluvial deposits here. Way down south at Aswan, the deposit depth is just 4 meters. But by the time it reaches Cairo in the delta, that depth swells to 9.6 meters. It's a perfect physical illustration of a river dumping its load as its kinetic energy fades.
Section 6. Human impacts and vulnerability. The AO2 synthesis.
Now, this is where your AO2 evaluation skills really come into play, because human impact has utterly devastated this delicate balance. Historically, the delta accreted or built up at a rate of 120 million tons per year. Today, accretion has fallen to practically trace amounts. The culprit is the Aswan High Dam upstream, which has trapped the sediment. This has created a massive imbalance, essentially starving the delta of its vital building blocks.
When you combine that sediment starvation with physical climate changes, you trigger a chain reaction of compounding threats. Global sea levels are rising at a rate of 1.2 millimeters a year. This means the coastal water is getting deeper. Deeper water produces larger, higher-energy waves that can now crash much farther inland. So a system that was historically a low-energy depositional environment is rapidly and dangerously shifting into a high-energy erosional state.
If you're writing an essay on human interactions within coastal systems, let this quote anchor your final evaluation. The uneven balance of river sediment combined with human impacts causes deltas to shrink, erode, and become more vulnerable. That is the exact analytical conclusion, directly synthesizing your AO1 facts with your AO2 evaluation that your examiner is waiting to read. So, I'm going to leave you with a rather provocative thought to chew on as you continue your A-star revision. On one hand, you've Yorkshire, actively battling relentless 4-meter waves. On the other, the Nile Delta, starved of its sediment and slowly sinking under rising seas. Ultimately, which of these drastically contrasting systems is truly the most fragile as we face an unpredictable future? Think deeply about it, keep making those connections, and best of luck with your studies.